Assalamu alaikum and very good day everyone. Today we will be presenting on the topic from planar MOSFET to FinFET, overcoming short channel effects and gate leakage in deep submicron CMOS scaling.
This is our team members.
Hi everyone, I'm Aidul Afiq bin Muhammad Hanif, matrix number 2210-11217 from Microelectronics Engineering.
My name is Afiq Jufri bin A. Jaafar, matrix number 2210-11216, and I am from Microelectronics Engineering.
My name is Zawawi bin Muhammad Zubair. My matrix number is 2210130000, and I'm from Microelectronic Engineering.
This presentation focuses on how CMOS transistor structures have evolved as technology scaled from micrometers to just a few nanometers. In particular, we will explain why the traditional planar MOSFET architecture started to fail and how the FinFET structure was introduced to restore electrostatic control, reduce leakage, and enable continued scaling. For over 50 years, Moore's law has driven semiconductor development. As we scale down transistor dimensions, we achieve higher performance, lower cost per transistor, and greater functionality. However, as the channel length goes below 100 nanometer and approaches the deep submicron regime, the physical behavior of MOSFETs changes significantly. The electric fields inside the device no longer behave ideally. The gate loses its control, leakage rises, and reliability becomes harder to maintain. The need for better transistor architectures became urgent because simply shrinking the planar MOSFET was no longer viable. The planar MOSFET is very straightforward. A flat silicon channel between source and drain, controlled by a single gate on top. For decades, this simple design scaled extremely well, but shrinking the channel length means the potential barrier that separates the source and drain becomes very short. The drain's electric field can penetrate more easily into the channel, and the gate cannot fully control what happens inside the device. This marks the point where undesirable effects, known as short channel effects or SCEs, start to dominate the device behavior. In deep submicron planar MOSFETs, three major short channel effects appear. First, drain-induced barrier lowering, or DIBL. Because the drain is physically very close to the channel, its electric field can lower the energy barrier at the source. The result is unwanted current even when the gate is off. This is a major contributor to increased power consumption in modern circuits. Second, threshold voltage roll-off. As the channel length is reduced, the threshold voltage drops. This means transistors turn on more easily than they should. When billions of transistors suffer from threshold variability, circuits become unpredictable and unstable. Third, sub-threshold leakage. Even when the gate voltage is below threshold, significant current flows because of weak gate control. This leakage dominates static power consumption, especially in battery-driven devices. All these issues appear because the gate only controls the channel from one side. The electrostatic control is simply not strong enough for nanometer scale operation.
Another major issue is gate oxide leakage. To improve gate control, the oxide thickness was scaled to below 2 nanometers. But at this thickness, electron can tunnel directly through the oxide due to quantum mechanical effect. This means the gate leak currents even when the device is supposed to be off. High-K dielectrics like hafnium oxide help, but they did not solve the core issues. The planar gate controls only the top of the channel. This is when the industry realized that scaling the planar MOSFET was no longer sustainable. To overcome these fundamental physical limitations, researchers introduced the FinFET. Instead of a flat channel, FinFETs use a vertical fin of silicon. The gate wraps around three sides of the fins, the left, right, and the top surfaces. This increases the contact area between the gate and the channel. Because of this three-sided control, the gate has much stronger influence over the channel potential. In the other words, the channel is now better shielded from the drain's electric field. This design directly tackles the root cause of short channel effects. FinFET solves short channel effect by wrapping the gate around the channel on three sides, greatly improving electrostatic control. The channel potential is now tightly controlled from the three surfaces instead of one. This dramatically weakens the influence of the drain's electric field, which directly reduces the IBL. With improved control the channel potential, FinFET achieve a steeper subthreshold swing and significantly lower leakage current. In addition, because the gate surrounds more surface area, FinFET can use slightly thicker oxide layer, which reduce the gate tunneling leakage. For instance, a 22nm FinFET was able to reduce gate leakage more than 50% compared to 32nm planar MOSFET. Together, this improvement allow FinFET to overcome the fundamental limitation of planar MOSFET in deep submicron scaling.
Industry adoption. In 2011, Intel introduced the first commercial FinFET technology at 22nm node known as the 3-gate transistor. This marked a major breakthrough for the industry. Soon after, companies like TSMC, Samsung and GlobalFoundries adopt FinFETs as their standard transistor structure for advanced nodes. As we approach the 3nm and 2nm nodes, even FinFETs begin to face challenges. The fins become extremely narrow, increasing resistance and variability. To push scaling further, the next step in channel structure evolution is the gate-all-around or GAA transistor. Here, the gate completely surrounds the channel, providing nearly ideal electrostatic control. This structure continues the same trend, transforming the channel geometry to fight short channel effects. So, in summary, planar MOSFETs worked well for many decades but failed at deep submicron nodes due to short channel effects and gate leakage. Second, FinFETs solve this issue by providing stronger gate control through a 3D tri-gate structure. Third, GAA device represent the next step in scaling, offering even better control for sub-3nm technologies. That concludes my presentation on channel structure scaling from planar MOSFETs to FinFETs. Thank you for listening.